talking about Rosetta Flash. Just very quick reminder that when talk's finished and you've given all the applause, on your way out, remember there's a box up there with some red and green cards. If you love the talk, grab one of the green cards, put it in. If you didn't like the talk, in the unlikely event you didn't like, go for the red card, but please, yeah, green cards in the boxes, that's what we like to see. Okay, thank you very much. It's Michele.
Hi everybody, I like green, just saying. So I'm here to present Rosetta Flash. And actually Rosetta Flash is, can you hear me well? Yeah. It's an exploitation technique that it's almost a year old. So this talk will actually focus, well, of course, on what it is, but also on what still works, what was not fixed properly, and how it is also useful now, how it can be useful now. And so I think most of you are already knowledgeable about JSONP and what JSONP is. So just to know how much time to allocate on that, I'm wondering how many of you know what JSONP is? If you can raise your hand. Okay. Great. I will just make a very short introduction then. So basically, there is this great technology. Oh, okay. It probably doesn't like. Let's try again. I will do it. Good. Okay, great. So JSONP is this great technology to bypass same origin policy normally, right? So basically, if you want to embed a script from another domain, you can do it with a script tag, right? And this is exactly what JSONP exploits, right? So if you want to execute JavaScript from another origin and you don't want to use like the proper way of doing that, you can use a hack, and this hack is embedding an external script, which is, for example, this one on LinkedIn.com, www.linkedin.com, count serve, count, share, and specify a callback. In this case, it's reflected callback, right? And the content of the reply will be at the beginning, reflected callback, which is the function specified, and then some data that is passed cross origin, right? It's the only important thing about JSONP that it's really important, crucial to understand Rosetta, is that the attacker controls the first bytes of the response, right? So you specify in a URL parameter the callback, and that callback is the first bytes of the response. Okay? So I try again to. Yes, it works. Great. So, but Rosetta Flash is about Flash, right? It's about Flash files. So Flash files normally are binary, and they are binary blobs. And in the callback parameter of JSONP endpoints, you can generally only specify alphanumeric characters, not binary bytes. So it would be cool if you could transform any Swift file to an alphanumeric one. And this is what Rosetta Flash is. Rosetta Flash is a tool that converts any Flash file to an equivalent one that is made only of alphanumeric characters. And why? Because as I said, there are different things that come into play. As I said, first, with JSONP, an attacker can control the first bytes by the callback parameter. And second, Flash files have this peculiar implementation of same origin policy. So if you can upload a Flash file to a domain, that Flash file can do authenticated requests to that domain, which means cookie carrying with cookies, right? Can read the requests and can also exfiltrate the results to an attacker domain. And this is by design, right? what we want to achieve is to have this without allowing if a user is not allowed to upload Flash files on that domain. So we're using a JSONP endpoint to reflect a Flash file. Because the Flash parser is actually very liberal and discards everything that it comes after a valid Flash file. So we just need to control the beginning of a response. And that's exactly what JSONP is. JSONP allows an attacker to specify the first bytes. But we need them to be alphanumeric, right? So if we just create an HTML page on attacker.com with an object tag with content type application extra wave flash and specify victim.com/JSONP endpoint, call back the Flash file, it's exactly equivalent to having that Flash file hosted on victim.com. Yeah, as I said, normally Flash files are binary. And how is it possible to make them alphanumeric? Like, it's kind of magic. Well, it's possible with compression. And not really with normal compression, but by abusing compressions. So Flash files can be uncompressed or compressed in two different ways, actually, what we see. But first, this is a valid Flash file, and it's made just of ASCII, alphanumeric, actually. And it is a rickroll. I would love to show it to you right now, but actually I shared this with Adobe and they fixed it. But not only that, if you have an antivirus software and you visit that, it gets flagged because they added a rickroll to their virus definitions. And sometimes they say W32, not sure why, Trojan rickroll. So this is just how antivirus vendors work, right? It's a bit weird. So let's just suppose that we have two domains, victim.com and attacker.com. So victim.com has a vulnerable, well, working as intended JSONP endpoint that just reflects the callback, right? This is PHP mostly because PHP is simple to write. I don't love PHP, but this just checks that the get callback is just made of alphanumeric and underscore, which is this \w in the regular expression, and it reflects it, right? And then adds open parentheses, open brackets stuff. Then an attacker can add on his malicious page on attacker.com an object type application extra code flash, and in data, victim.com, vulnerable JSONP, callback, and the alphanumeric flash file, right? So the JSONP endpoint will reflect the alphanumeric flash files. It will be, the browser will think it is a valid flash file because we force the application extra code flash content type with the object tag. And well, then we have some other values in the Flash variables because actually this is no longer a rickroll. This is a universal exfiltrator. So this is very, let's say, weaponized in a way, proof of concept where you can specify a URL you want to access with the victim's credentials, so with the cookies and everything, and where to exfiltrate the content. Okay, so it accepts like a URL variable. The URL in the same domain of the vulnerable endpoint to perform a GET request to, and exfiltrate an attacker control URL to which post a variable with the exfiltrated data. On my GitHub, which is that one, there are several more. You can execute arbitrary Flash code. So there is an eval, for example, action script, which is ready to download. And almost all of the web, modern web, was or is vulnerable. So Google, Yahoo, YouTube, LinkedIn, Twitter, everything. Just because they use JSONP, right? They don't do anything wrong. They just use JSONP. And the combinations of these things create a vulnerability. Facebook and GitHub were actually safe because they already employed a mitigation thinking that one day it might be possible to have alphanumeric Flash files. And so they were very, let's say, prudent in that. In particular, I would like to thank Alok, like ex-Facebook security, who wrote a great blog post about trying to achieve alphanumeric Flash files. That was great inspiration for me. And that's also why he patched Facebook, basically. Google in particular was vulnerable on important domains such as www or accounts. So accounts.com could exfiltrate the tokens, for example, so you could take over an account. Books, maps, and they're all fixed, and we'll see how. So a step back now. This is basically how a Swift header looks like. There are three types of Flash files: an uncompressed one, a zlib compressed one, and a LZMO compressed one. SLMA, sorry. So it first starts with Swift reversed, FWS, or C for compressed if it is compressed with zlib, or well, Z if it is LZMA. But we can ignore the uncompressed and the LZMA because we will focus on zlib. What is zlib? Zlib is basically a wrapper over deflate with a header and a checksum, right, for integrity. We'll see later. If you are into specifications, you can read RFC 1951. And then you have to read 1950, which is deflate, because basically zlib says, yes, it's deflate with a header, so you have to get back and read and study deflate. One very good thing is that Flash parsers are very liberal, so they allow invalid fields. So for example, in the version field, you can put like an alphanumeric character, and it will accept it. Same for file length. Well, you don't have to put a very high byte as the rightmost, because it's the most significant one. And if you specify a very high one, at least in Chrome, it would not execute, because it would try to allocate too much memory, and then it would refuse to execute. But that's, I mean, you can put a 0, which is fine for us, and it is the lowest allowed ASCII, right? And it would work, right? So you can put like chow 0, and then you have zlib data, right? That incorporates also a checksum. So we want to make it completely alphanumeric. And we want to make the checksum alphanumeric too, right? Because it is part of the file. So we already see that we have levels of, it's a bit meta, right? Because we want to create something that is alphanumeric, and we want to define inside of it tables for the decompressor to make it alphanumeric. And the tables themselves, because they are embedded, have to be alphanumeric. And the checksum has to be alphanumeric. So it's a bit difficult. It's a difficult problem. So well, basically deflate does two things: duplicate string elimination and bit reduction. I really don't want to spend time on the details of deflate, because I think they would actually take away a bit from the big picture. But feel free to ask me anything, like whenever. I would love to. So basically zlib has this header. So the first byte is basically compression method, and for the 4 bits, and then for the other 4 bits, compression info. So good news, we can make the first byte to be an alphanumeric character, which is compliant with the format. So for example, lowercase h is fine. It's an 8 for compression method, and the second one is actually a window, but it works. The second one is a little bit more tricky because it's basically also a little bit like a checksum. It has to have a modulus 31, which is equal 0 together with the byte before. So I just ran a very simple script to try to brute force the possibilities, and it looked like h, lowercase h, and capital C is good. It works. It's a valid zlib signature. It's one of the very few, actually, that are valid. So we got that part sorted. So we have a valid zlib header. We used to have a valid Swift header, right, because the parser is relaxed, and now we have a valid zlib header. Then, inside there is deflate, right? And deflate is a block compressor. So you have several blocks, and each block is a kind of a matryoshka, right? Has the first bit, which is it the last block? Then we have like 2 bits that say this is dynamic Huffman, so you specify your own tables. For what a table is, feel free to look at the specification. It's basically something that translates bytes to other bytes, and this is something that we'll use. In this case, it always has to be dynamic Huffman. Then there are some numbers, some counters of the number of literals, number of lengths. We won't go too much into detail. Then there are 3 tables. The most important one is the first one, the length of lengths, which says translated this code to that other code. And then there are, well, 2 more. And then there is an endo block code. Okay? So we don't care about compression. Actually, what we are doing is mapping a binary file to another file that is made of a more restrictive char set. So it can't be a compression, right? It has to be an inflation because we are basically reducing the entropy of the char set, right? So we are actually using a compressor to inflate something. This is already a bit weird. But not only that, we also have, 2 main problems. Creating a tables actually that work, so they guarantee that the output is alphanumeric, and making sure that the checksum itself is alphanumeric. The checksum is of the uncompressed Swift file, okay? And how does the checksum work? It's an Adler 32 checksum, which is a very lightweight checksum. It's not polynomial based, so it's not like CRC, for example. It's just 2 rolling sums, 2 bytes rolling sums, S1 and S2. So for every byte, it can also work as a rolling sum, so it can be computed dynamically, right? For each byte you add, for each byte B you add B to the first rolling sum, S1, and then you add S1 to S2. And S1 and S2 are, of course, modulus 65521, which is the largest prime less than 2 to the power of 16. So we want to make both S1 and S2 alphanumeric, and we control the original uncompressed Swift files. If you remember, I told you that the flash parser ignores any trailing byte at the end of a valid flash file. So we can append every byte we want. So we can exploit this malleability to create a ad hoc checksum, right? But what is the most clever way of doing that? So just one way of doing that, that's what I used, is having a high byte sled, in this case FE, for example, so that we overflow S1. So we want S1 to be alphanumeric. So alphanumeric is usually a kind of low byte value, right, because of the ASCII table. So we overflow it, and then we add the first delta, which is delta 1, just to make S1 what we want to be, like an A, a B, whatever, right? Then we want to keep S1 fixed, because we want to update S2 and make it also alphanumeric, but we don't want to also change S1. So a very simple way for not changing S1 is adding null bytes, because every time you add a byte, it adds to S1. So if you add 0, S1 doesn't change, right? So if we add 0, S2 becomes S2 equal S2 plus S1, okay? And then we can add another delta, we can call delta 2, that basically gets the S2 we want. So it's actually pretty easy with this SLED technique to get an alphanumeric checksum. So now that we know that we can manipulate the file to get a checksum, how we want it to be, we need to use Huffman to actually encode the file to be alphanumeric, so to get bytes, binary bytes, and transform them. So I use 2 different encoders, and credits for the tables go to Gabor Moller. So basically, I don't know if you can see, yeah. So for example, code 16, I put length 2. This means that code 16 becomes 0, 0, which is the first in lexicographic order for a length 2 code. But anyway, The thing is, this thing tells the decompressor how it should decompress, but also the table itself has to be alphanumeric because it's included. So that was pretty hard to achieve. This was something like really, really, really hard to achieve. And we don't care about efficiency. We don't care about functionality. We just want something which is valid and that generates alphanumeric bytes. So we care about the disalignments, what I call disalignments. So we want, in a way, it's like kind of poetry. We want a kind of rhythm that every beat after 8 bits, it returns a character if you cut there, right? So, for example, sometimes I had to specify something in the table that does not do anything, just to make the table itself be alphanumeric. Okay, actually most of the table is unused. It's just to make it alphanumeric. So this is how it looks. Thanks to Frank Yellen, by the way, for this debugger, who greatly helped me in developing this. If you don't know, Frank Yellen is one of the Java guys, one of the creators of Java. It made runtime exception. If you hover on Eclipse on runtime exception, you see his name. It's pretty cool. So you can see that basically after the colons, you see that byte in ASCII, what it is. So what we care about is making them alphanumeric. And you can see that, for example, the first one is a 0, then there is a P, oh yes, also the bit order is a bit weird. Sometimes it's LSB, sometimes it's MSB, so sometimes it's just a bit weird, because inside of Deflate there are some things that are in MSB order, sometimes they are in LSB order. But anyway, you see that, for example, we have D0, U, P, 0, right? And this is what it has to do. So basically, wrapping it up, we have a signature, and the signature is ASCII, and that's fine. We have a version, and we can put whatever we want there. So that's ASCII, that's alphanumeric. And we have a file length, same. The zlib data, it's alphanumeric thanks to the tables. And the checksum is alphanumeric because we can manipulate the original flash files by adding bytes at the end, right? So with the sled and delta techniques. So mitigations, I would like to talk about mitigations because this is actually, is it kind of clear what I said so far? Because it's kind of complex and I don't want to dive in too much into the details, but really feel free to ask me everything, especially at the end if you want. So it's very hard to mitigate this because it's basically nobody's fault. It's kind of a confused deputies problem. So it's not Adobe's fault, right? Because that's just the format. It's not the browser's fault because, well, plugins. It's not website operator's fault because JSONP works like that. JSONP is supposed to reflect the callback, right? So I think Rosetta is a great example of how combining several things that work as they should work can create a vulnerability. I contacted Adobe in May of 2014 when I discovered and I had a working universal proof of concept. And they pushed this fix, which I couldn't check, but it was pushed after almost 2 months because there was the World Cup, so they were afraid of breaking the Flash player. Because everybody was apparently, especially in South America, everybody was watching like with Flash the final. So I understand that, priorities, right? So what he did is check the first 8 bytes of the file, and if there is at least one JSONP disallowed character, which is a string definition, then the Swift file is considered safe. And no further check. Otherwise, they check the first 4K of the file. And if there is at least one JSONP disallowed character, the file is considered safe. Otherwise, it's considered unsafe, and it's not executing it. Okay? This was not enough. So the JSONP is allowed list was basically the negation of alphanumeric and point and underscore. But this is too broad for most real-world JSONP endpoints. Because a lot of them, for example, allow the $sign because of jQuery and other fancy JavaScript library. So if you add $sign to the allowed char set of Rosetta Flash, you would bypass the fix very easily. But you actually don't have to do that. There's a slightly more subtle way of doing that. It's by exploiting something that naturally occurs in the response of a JSONP endpoint, which is a parenthesis. So after the callback, there is always, in the reflected callback, there is always an open parenthesis, because the callback is a function, right? So what you can do, and what is the last byte of the Flash file? It's the least significant byte of the checksum. But what is said is that the checksum, you control the checksum. The attacker controls the checksum. So we can make a Flash file that, as the last byte, has an open parenthesis. We can. And what can we do if we do that? We would pass to the callback the Flash file except the last one, except the open parenthesis, right? Which would be there in the response, so it would work anyway. And so we would have a response with a full value sweep file, and it would work. It would bypass the fix, because it would see there is an open parenthesis, which is JSONP disallowed, and it's not in the request, it's not in the parameters, so it would bypass the fix. So the fix was bypassed like actually in 1 hour of work into looking at that. And so there is a better way of fixing it, and this is the current one. I don't have access to Flash source code, so I had to do it the hard way. But luckily, they have symbols for the debug edition. So check header, you can see what is that check JSON bytes. You can see that there was a fix for Rosetta here. So what is they're doing now, it's a much better thing. They're looking for content type, application X/Wave Flash, and if there is, it's considered safe. Wait, this means the content type returned by the server. Because a JSONP response, typically it's application JSON content type that is overridden by what you specify in the object HTML tag. So you're forcing a content type. Okay? So if it's natural, the server naturally returns application X/Wave Flash, it probably means that it's a legitimate Flash file. So this is a preliminary check. Then they're checking the first 8 bytes, and if any bytes is greater or equal than 0x80, which is non-ASCII, then okay, then the 4K, okay, otherwise it's unsafe, it's not executed. This is much better because they are not basically blacklisting, they are kind of whitelisting in a way, right? And this is much more robust. Last time I presented this, I said that's endgame, right? And we should talk about mitigations by website owners. But actually, it's not enough. This is not enough. This can be not enough. So can you think of a way in which something that is actually has at least 1 byte which is greater or equal than 0x80 would still be text in a way? Can you think of anything? Unicode, right? UTF-8. So UTF-8 has sequences of bytes, right? So if we have, for example, a 2 byte sequence, it can easily be that one of the two is like C0, for example, right? And the other is something else. So if the JSONP endpoint allows UTF-8 characters in the callback, then we can very easily bypass this. Because, for example, E with an accent, it's like C0 something. So if the JSONP endpoint allows it, then we bypass it. And it works right now. You might say, why should a JSONP endpoint accept UTF-8, right? But they do. Actually, I would say like 20% do, okay? Even in very important services. And I'm not saying which one, but very important ones. So what can website owners do to mitigate this? Because nobody will, not enough people will touch Flash, right? Mostly because it's hard, the adoption curve, the update curve for Adobe Flash is pretty slow. And that's mostly because, well, it's hard to update, it's hard to keep updated. On Windows, there are software bundled with Flash updates, which make a lot of people, even savvy users, decide not to update it because they don't want to install McAfee, for example, together with that. So what you can do as a website owner, you can return content disposition attachment, which forces a download of a JSONP response, which is perfectly fine for its normal use, but it prevents plugins to interpret and execute, at least since Flash Player 10.2. Or you can do something which is actually what most sites are doing and web frameworks are doing, so Google, Facebook, and also Ruby on Rails, MediaWiki, they all fix it this way, to prepend an empty comment block like this before the reflected callback. So basically you would make it not a valid Flash file because you control the first bytes and you no longer control the first bytes. Even a space would be enough. So even if you return space reflected callback, the attack would not work. Okay? In some cases, X content type options no sniff also prevents plugins for interpreting this as Flash. Not always. So this is not the best thing. So in conclusion, I think this exploitation techniques that allows basically exfiltration of data, XSRF, and same origin policy bypass demonstrates that it's not always easy to blame vulnerability on somebody. It's very hard to see who's the culprit of this. It could have been solved at different stages, like when parsing the Flash file, for example, but you don't have to be overly strict, because otherwise you would break legitimate Flash files. So that was Adobe's main concern, and that's very understandable, right? By the plugins or the browsers, by, for example, employing strict content type checks, so refusing to execute if content type is not Shockwave Flash. But then a lot of web browsers have broken content types. A lot of web browsers, for example, return application octet stream for Flash files. So that will break really a lot of things. Or, of course, website owners. Website owners could prefix anything to the reflected callback. Anything that is, of course, semantically void in JavaScript to the reflected callback. And with this, I am done, and I really hope to have a lot of questions. Thank you. Tell me.
Good question. Does the current version that you have on GitHub work against the latest Flash patches or not?
No, so Adobe fixed that. Well, it depends. Okay, so it's Rosetta Flash has this variable which is allowed charset. Right now it is restricted to alphanumeric and underscore and dot. So like this, it would not work because Adobe would refuse to execute such a valid Flash file that is made only of those characters, right? It's like basically a stubborn kid. But if you have, for example, a UTF-8 accepting JSONP endpoint, what you can do is putting all valid to sequences Unicode in that variable, allowed charset, and then it would work because Flash is not blocking that, right? I mean, the only thing that makes it not work is the fix by Adobe and by website owners by prefixing. So, for example, if you check Facebook, Google, Twitter, they no longer return the callback without anything before them. But for example, some websites do still. But for example, LinkedIn decided not to prefix anything, but they added a no sniff header, which is enough for modern browsers, not for old. And then like credit cards companies do not care. I reported both of them like 1 year ago. But LinkedIn replied. American Express did not.
But my question is,
Mhm.
the tool that you have on GitHub,
Yeah.
does it allow you to configure like the UTF-8 character set so that the login?
It's just a variable allowed char set, and if you put there, for example, a range instead of thing, then you can run it and it will generate something that has.
So it's not click and go, but it's almost there.
Well, it can be click and go very easily. I mean, it's just one line of just putting a UTF-8.
Take one variable.
Yes, exactly.
Okay.
Because I'm not distributing. I mean, I'm a responsible researcher. I'm not distributing.
Yeah, no, I'm interested because I have a test where this could be a vulnerability. So.
Well, there are actually several places where it could be still a real vulnerability. So, for example, I've been told that, for example, the load movie in Swift files, it looks like it's not doing the same checks. So if you have a Swift file in which you can inject the content of a load movie call, load movie basically loads a Swift file and executes it. It's basically the eval of Flash. No, well, it's not an eval. It's an embed of Flash, right? It looks like you can use it for basically bypassing the same origin policy if you have such a scenario. But then you would have to have a vulnerable Flash files in the first place.
Yeah.
Well, this applies to anything and everything, right? Other questions?
If you want the technical details, where can you find them?
Oh, okay. So basically, if you go to my blog posts, you search for Rosetta Flash, the first result, you will see more. So you'll see a little bit more technical details. Also, the RFCs for deflates are useful. And ultimately, read the code of Rosetta Flash. It's Go. So you might learn a new fancy language too. And feel free. It's not too complex also. It has something a bit hard-coded, but I tried to comment the code. So it's commented. So yeah, please.
Was there anything different that needed to be done to make the CLIB and the checksum data pass validation for UTF-8 versus anything under OX80, like just versus under ASCII?
No, it's completely the same. Because you can add arbitrary content at the end, so it really doesn't depend on what was there.
Okay.
You could have anything, and you would eventually overflow it and get down to the value you want. It doesn't matter, yeah. No, completely the same. Really, you just really have to change one variable. Everything else works. Yeah. Also because that checksum is of the uncompressed Swift files, which was binary. It was not ASCII in the first place, right? So it's the most general case you can. Anything else? Thank you.